What is a railgun? A railgun is a device that uses electromagnetic force induced by a pair of conducting rails to launch projectiles. The projectile is placed on the rails, generating current through the projectile and creating a magnetic field that causes the projectile to accelerate forwards. For instance, the railgun shown here was built for the U.S. Navy and is capable of shooting projectiles at 5,600 miles per hour. That's 2,500 meters per second. However, the railgun we have built for this project is much less powerful. To build this railgun, we took a piece of cardboard and glued 2 strips of aluminum foil to it at a distance of roughly ½ an inch apart. We then taped 2 wires to the aluminum foil and attached the other ends of each of the wires to alligator clips. To make our projectile, we attached 2 magnets at opposite orientations to a piece of steel wire. To operate the railgun, we attached the positive port of the battery to the strip of aluminum foil on the right-hand side and the negative port of the battery to the strip on the left-hand side. Once the projectile is placed on the track, it will begin to accelerate due to the current running through it as well as the magnetic forces induced by the current in the foil. To see how the railgun works, you have to use the right-hand rule. If the correct ports of the battery are attached to the correct strips of foil, then the current will flow in this direction. According to the right-hand rule, this current will then induce a circular magnetic field that points out of the cardboard in the area between the foil rails. The right-hand rule can then be used to determine the direction of the magnetic force exerted on the projectile. Since the current runs from the right-hand rail to the left-hand rail, and the magnetic field is pointing upwards, the force exerted on the projectile must therefore be pointing to the left, in the opposite direction from the battery. In theory, this would cause the projectile to accelerate in this direction. However, the magnetic force induced by the battery is extremely small, and its effects are minimal. So what actually causes the projectile to move? The answer is that the current generated by the battery actually creates a torque on the magnetic wheels of the projectile. Because the magnetic wheels are facing in opposite directions, the magnetic field they generate looks like this. The right-hand rule can then be used to find the direction of the force exerted on the wheels. Since the current is flowing along the right-hand foil strip and the magnetic field is pointing away from the wheel, the force exerted on the magnetic wheel must therefore be pointing out of the cardboard. This generates a torque that causes the wheels to turn, in turn causing the projectile to move forwards along the rails. After building the railgun, we used Tracker to determine the acceleration of the projectile by tracking the displacement of one of its wheels, graphing its velocity over time, and finding the line of best fit of this graph in order to determine this projectile's acceleration. This graph suggests that the railgun causes the projectile to move under the influence of a constant acceleration of 0.13 meters per second squared. It is important to remember that the extremely small forces involved, as well as the wealth of opportunities for human error, threaten the validity of this measurement. However, one thing that's certain is that we probably won't be seeing railguns like this anytime soon outside of sci-fi.